All right, everyone. Welcome to lesson 31 of Calculus 1. Today, we're going to talk about what's called the net change theorem. Now, this is actually already something that we've seen in the previous lesson. So in the previous lesson, I gave an interpretation of derivatives and integrals, which in a certain sense are opposite operations because we have the fundamental theorem of calculus. So integral or integrals represent the net change in a function between a and b. So if you take the integral of f prime of x between a and b, then it'll be the difference between f of b minus f of a. And this is what's known as the net change. And in many cases, this will be equal to the total change. But as we'll see, sometimes the function wiggles back and forth in this region before reaching its endpoint. So often the function can be doing a lot more than appears right here. We'll see an example of that in a moment. So what does this mean? It means that if we know the rate of change of a function, then we can integrate it between 2 points and find out the total amount or the net change of our function. So for our first example, let's suppose a population has a rate of change, and we'll call this p prime of t equals 2t plus 5. Find the total change in population over the first 2 years. By the way, this is in units of people per year. So we're going to find the total amount of change in the first 2 years. So what we do is we integrate from 0 to 2 of whatever our derivative is. So in this case, we're going to integrate from 0 to 2 of 2t plus 5. Now, as we saw in the last lesson, we don't need to worry about crazy Riemann sums anymore. And even though we could do this one using geometry, this is a straight line, so we can use triangles and rectangles to get the area under the curve. We now have a much easier way of finding the area of the curve. And that's finding the antiderivative of this and then plugging in these two numbers, aka using the first version of the fundamental theorem of calculus. So we end up with t squared plus 5t as our antiderivative. And then we put 0 to 2 right here. And then I plug in 2. So I have 2 squared plus 5 times 2. And then I subtract and I put 0 in here. But as with every polynomial, when I plug 0 into there, after we get out of an integral, it's going to end up giving us 0. So we end up with 14 as the total amount of change in our population. Now, notice that this only gives the amount of change. So this doesn't say like, oh, there are 14 people in our population after 2 years. All this says is that there are 14 more people in year 2 compared to year 0. So for example, if there were 100 people in year 0, then there'd be 114 people in year 2. If there were 1,000,000 people in year 0, there'd be 1,014,000 in year 2. Remember, this gives you the amount of change. It doesn't necessarily give you any specific value. To know what that specific value would be, we would need to have some kind of data about the original function, like p of 0 equals some number. Okay. This is actually going to be a relatively short section. We really only have 2 examples left. So suppose that the velocity of some particle is given by sine of t. So this is a situation that might be encountered in, say, spring motion, where an object oscillates back and forth. This might be where we have a velocity being a periodic function like sine. So what we want to do is we want to find the change in position from t equals 0 to t equals pi. All right, so the change in position will be the integral of the velocity. By the way, the change in position is known as the displacement. All right, so we have the integral from 0 to pi of sine of t. All right, now the antiderivative of sine is negative cosine, and then we'll be plugging in 0 to pi. So I plug pi in for cosine. I have negative 1 minus negative cosine of 0, which will be 1. So all in all, for this, we end up getting 2 for our answer here. So it seems like this particle changed position 2 in the forward direction. Okay, now let's repeat this question, only we're going to go from t equals 0 to t equals 2 pi. Let's see what the change in position is then. So 0 to 2 pi of sine of t, you'll end up getting negative cosine of t from 0 to 2 pi. And then I go ahead and plug 2 pi into here, and I have negative 1. Then I subtract, I plug 0 into here, I also get negative 1. But negative 1 minus negative 1 will actually end up being 0. So what this means is that this has 0 displacement over 2 pi seconds, or whatever our time unit is. Now, at first, this might seem kind of strange because we know that the particle moved 2 in the first pi seconds, but then somehow it's 0 away from where it started and the next pi seconds. So what happened here? Well, it turns out that this is an illustration of the difference between displacement and distance. So using the net change theorem gives us displacement, but if we wanted to find out how long it traveled altogether, its distance, then what we would need to do is we would need to put an absolute value for this. So if we want to know distance, this is what we would do instead. And what would happen is that sine is positive from 0 to pi, so we don't need the absolute value there, but it's going to end up being negative. So we have a negative sign from pi to 2 pi. All right, then this will end up giving us our distance. So we integrate from 0 to pi for sine of t, and we actually already saw what happened with that. That's going to give us 2. And if we then look at this right here, we have sine of 2, or sorry, this will integrate to cosine, negative cosine. And then we have 2 pi and pi right here. We integrated the negative cosine, making this be positive. Then we have 2 plus cosine of 2 pi will be 1. And then we subtract cosine of pi, which is negative 1, giving us a distance of 4. So this is a subtle difference between net change and total change. So 4 is the amount that our particle has changed altogether, but some of the change is canceled out with one another. In fact, it equally cancels out. So the net change of the position of this particle is 0, but the total amount of change is equal to 4. Now, in the previous example here with population, the net change and total change ended up being exactly the same thing because the absolute value of 2t plus 5 is 2t plus 5, at least in this interval right here. So this is a point where, this is a situation where the net change and total change were the same, but in this situation, we had a net change of 0 and a total change of 4 because part of the change, the particle went 2 to the right, but then it immediately went back to the left. So some of the changes in the particle's position canceled out with one another, 0. All right, so that's about it for this lesson. I just wanted to show you how the integral represents the net change. And we could also write here integral from a to b of f prime of x dx, which may end up being more complicated. That will be the total amount of change. So how much the particle is moved altogether, if we imagine it. All right, well, that's about it for this lesson. So I will see you guys next time for our final lesson.